Hello students, today we will study Fourier series, and to understand Fourier series in better way, two things we need to understand first. First is periodicity and second is orthogonality. So what is periodicity? Any waveform is said to be periodic when it repeats itself after a duration t. So suppose this is one square wave. This is square wave. This is the shape of this square wave, and if suppose it is repeating, this is suppose 1 second duration square wave. So after every 1 second, suppose it is repeating itself. So after 1 second, it will end at the second cycle will end at 2 seconds. This is 2 seconds. The duration is 1 second. So we will say that this square wave has a time period of 1 second, and its fundamental frequency denoted by f0 is 1 over 1 second, that is 1 hertz. So the Fourier series claims that any periodic signal, in our case this square wave, let us assume is a square wave of 1 second. So any periodic signal can be reconstructed or decomposed into sines and cosines of different frequencies. So let us see what it actually means. So before going to that claim, first we need to understand that any periodic signal, suppose this is 1 hertz signal and another signal which is having a duration frequency of 0.4 hertz. So if we add two periodic signal, what is the resultant signal? Is it periodic? If yes, what is its period? It is very important to understand this concept. So suppose we are having these two signals, 1 hertz and 0.4 hertz. Let us plot these two signals with respect to their time. So this is time axis for first signal, that is 1 hertz signal. So you are having 1 second, 2 second, 3 second, 4, 5, 6, 7 and so on. Suppose the signal duration is, its frequency is 1 hertz, so duration will be 1 second. So this is the first cycle of first 1 hertz signal. This is the second cycle, will start from 1 and end at 2. Third cycle will start from 2 and end at 3. This is fourth cycle, this is fifth cycle, like this. Now the second signal, let us assume it is a 0.4 hertz. So 0.4 hertz signal will have the duration of 1 by 0.4, that is 2.5. So 1, 2, 3, 4, 5, 6, 7. Now 2.5 means, so the first cycle of second signal, that is 0.4 hertz signal, will start from 0 and end at 2.5. This is the first cycle. The second cycle of this signal will start from 2.5 and end at 5. So by the time the first signal is completing 5 cycles, the second signal only completes 2 cycles. And this time is very important, this 5 seconds, because they both are meeting here. Means if we add these two signals, then the combined time period of the signal will be 5 seconds, because after 5 the cycle repeats, that is somewhere at 10 seconds again they will meet. So the combined duration of the signal will be 5 seconds. So frequency will be 1/5, that is 0.2 hertz. Like this, any signal, suppose 1 hertz signal is there and we have added it with 2 hertz signal, so the resultant signal will have frequency of 1 hertz only, because 2 hertz signal will complete 2 cycles, and by that time 1 hertz only will complete 1 cycle. Likewise, 1 hertz multiplied by 5 hertz, added 1 hertz added with 5 hertz will again have frequency of 1 hertz only. So if you add any frequency 1 hertz with integer multiple of 1 hertz, the resultant signal will have the frequency of 1 hertz only. This n is integer multiple. Suppose you are having the fundamental frequency of 2 hertz, and if 2 hertz, if we add integer multiple of 2 hertz, the resultant signal will contain or will have the basic fundamental frequency of 2 hertz only, that is 2 plus 4 or plus 6 plus 8 plus 10. All the signals will have, the combination of all the signals will have the frequency of 2 hertz only. So the claim of Fourier was that any signal, any periodic signal, any periodic signal can be reconstructed by using infinite number of sine and cosine functions. So let us assume our periodic signal that was having 1 second duration. So this is our periodic signal, square wave, having duration of 1 second. For negative also, let us assume the amplitude is 1 here and the duration is 1 second, that is this is 1 second, this is 2 second, like this. So the claim of Fourier is this signal can be represented by sine and cosine functions. So this signal, let us assume it is ft. So ft can have frequency of 1 hertz, because its time duration is 1 second. So fundamental frequency of ft will be 1 hertz. So if we assume that the signal is having 1 hertz component, it is frequency axis, it could have 2 hertz component also, it could have 3 hertz components, it could have 4 hertz, 5 hertz, that is integer multiple of 1 hertz. All these are integer multiple of 1 hertz. If we add, the resultant signal will be having frequency of 1 hertz only, because addition of integer multiples of this frequency will not disturb or corrupt the duration, that is 1 second. But if we add 1 hertz signal with 1.5 hertz signal, it will not be 1 hertz signal anymore, that is the duration will be corrupted. Duration, that is 1 second, is now distorted. So we can add integer multiples. So this spectrum, this 1 hertz component will certainly have any values. Let us suppose it is B1. 2 hertz component will have certain value B2. 3 hertz component will have certain value B3. 4 hertz B4. 5 hertz B5, like this. So Ft could be represented by infinite number of sines and cosines. So let us assume it is sin B are the coefficients of sine. So we can write B1 sine 2 pi, 1 hertz component means 1t. Then B2 sine 2 hertz component means 2t, plus B3 sine 2 pi 3 hertz component means 3t, and so on. So we can approximate it like summation n from 0 to infinity Bn sine 2 pi nt. So this is Ft in terms of sinusoids. Also, it could have cos components. Actually, basically these sine components are representing the odd part, because sine is an odd function. We know sine of minus theta is minus sine theta. So if signal is purely odd, we have to only calculate this bn's. But if signal is even, then we have to calculate another set of coefficients known as an. So this could be the spectrum of the even components. So this is F. It could have 1 hertz component, 2 hertz component, 3 hertz component, 4 hertz component, like this. So 1 hertz some amplitude, let us suppose it is A1, 2 hertz component, suppose it is A2, 3 hertz component A3, A4, like this. So we can represent it by A1 cos 2 pi 1 hertz component plus A2 cos 2 pi 2 hertz component 2t, then A3 cos 2 pi 3t, and so on. So Ft could be like this also. So depending on the nature of the signal, whether it is even or odd, we have to calculate the coefficients. So it could be also generalized as n from 0 to infinity an cos 2 pi nt. There are some signals which are neither odd nor even. So the signals which are neither odd nor even, neither or odd nor even, for these signals we need to calculate both an and bn. So in that case the ft will become combination of an cos 2 pi nt plus bn sin 2 pi nt n from 0 to infinity. Now the question remains how these values of an and bn is to be calculated. So to calculate an and bn we need the concept of orthogonality. As I said in the start of this video that these concepts periodicity and orthogonality are very important, out of which we understood what is periodicity and how the adding integer multiples of fundamental frequency doesn't change the duration of the signal. Likewise, the orthogonality is also important. So let us understand what is orthogonality. So function f1t and f2t are said to be orthogonal if their product integrated over time t is 0, then they are called as orthogonal. So it's just like the resolution of the vector. If you recall from vector theory that x-axis, y-axis, we generally tend to resolve this vector on x-axis as well as on y-axis. The condition was y and x should be 90-degree apart, that is these were called basis functions or basis vectors. So here also the same thing is being done with respect to signal, that any function f1t and f2t, they are said to be orthogonal if their product integrated over time t is 0. Now according to claim of Fourier, we are going to resolve our signal or decompose our signal into different sines and cosines. So we have to check whether sine and cosines they are orthogonal or not. So you can check it analytically or graphically. Just for the sake of understanding, we'll do one simple graphical analysis. So let us assume that two signals are there, two sinusoids we'll draw. So suppose this is one sinusoids, this is one cycle, this is two cycle. Suppose its frequency is 2 hertz. Let us assume its frequency is 2 hertz. Now another signal having the frequency of 1 hertz means what? The frequency is half of this, means the time taken by this signal to complete 2 cycles, here it will be only 1 cycle. So only 1 cycle will be covered because its frequency is low, that is 1 hertz. It is exactly double of this. Now if we multiply these two signals, then what is the result? Let us see. We are multiplying these two signals over time t. So it is positive, it is also positive. here it is 0, so here it will become 0 starting from 0. So it at maximum position will be like here, because here it is also maximum, here it is also maximum, so the signal will be like this. Next, for this duration it is negative, it is positive, so the resultant signal will be negative. Now here it is again negative, it is positive, so resultant signal will be again negative. Here it is negative and it is again negative, 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 positive, so resultant signal will be like this. Now if we want to calculate the integration of this product, means what, we are calculating the net area under this curve. So this sine 2 hertz signal, we can represent it by sine 2 pi 2t, and it is sine 2 pi 1t, and this is nothing but integration over time t sine 2 pi 2t multiplied by sine 2 pi 1t dt. The effective area is 0. You can also verify it by analytically. So for any signal, if you assume it is 4t, then again the result will be 0. The generalization we can write integration over time t sine 2 pi mt multiplied by sine 2 pi nt dt. The result will be 0 for m is not equal to n, and it will be 0.5t when m is equal to n. You can verify it analytically. In our square wave case, if you substitute here 0 to 1, then you can see it is 0.5 only, because time was only 1 second. So whatever quantity is there here, the half of this will appear here. So this is what we are concluding, that sine functions are orthogonal. So like this also, sine and cos, sine 2 pi mt into cos 2 pi nt, the result is 0 for all m and n. Of course m and n are integer. So we can say that sine and cosine, they both are orthogonal. Again, cos function with other cos functions having different frequencies, they are again orthogonal for m is not equal to n, and it is again 0.5t for m is equal to n. Of course if it is 0 to 1, then t is 1, so it only becomes 0.5, but in generalization you will write 0.5t. So when m is equal to n, in either of the cases except this term, here for all n and m it is 0, but for this case and this case, two cases, when m is equal to n, what is happening, the signal is getting multiplied by itself, that is cos 2 pi mt multiplied by cos 2 pi mt dt. So signal is multiplying by itself, so it will become cos squares something 2 pi mt, and we can represent it by 1 plus cos 2 into that 2 pi mt. divided by 2. So this 1 by 2 is getting outside, and this 1 by 2 we are representing by 0.5. So like this the result comes. You can do it analytically and verify. So the conclusion is, in order to calculate our ANs and BNs, what we are doing, AN, suppose we want to calculate AN, what we are doing, we are taking integration of our signal ft with cos 2 pi nt dt. What is this operation? This operation is called as correlation. Finding the correlation. What is our assumption? What was our assumption is that ft contains different sinusoidal components like 1 Hz component, 2 Hz component, 3 Hz component, 4 Hz component, like this. So 1 Hz component is, suppose, cos 2 pi 1t. 2 Hz component will be cos 2 pi 2t. 3 Hz component will be cos 2 pi 3t. Let us assume we want to calculate A1. A1 is nothing but 1 Hz component inside f of t, and 1 Hz, which component, even or odd? It is, of course, if it is A, means we are representing it by cos, so of course it will be even component. So 1 Hz even component inside ft, which is nothing but A1. So what we are doing for calculating A1, we are multiplying ft by cos 2 pi 1 Hz t dt, because our signal, so we are multiplying ft by 2 pi 1t in order to find 1 Hz component inside ft, that too even. So this operation, what will happen, the result of this operation, because ft is having different components, 1 Hz, 2 Hz. 1 Hz component represented by cos 2 pi 1t. It will have cos 2 pi 2t. Of course, there will be infinite number of components inside ft. 1 Hz, 2 Hz, 3 Hz, 4 Hz, like this. But when we are multiplying this cos 2 pi 1t, which component will respond? Only this component. All the other components will result in 0 because they are orthogonal. Cos 2 pi 1t is orthogonal to cos 2 pi 2t, is orthogonal to cos 2 pi 3t, is orthogonal to cos 2 pi 4t, and all the other components except cos 2 pi 1t. So actually what we are calculating A1, which is nothing but 1 Hz component inside ft, and it is integration of t over t ft cos 2 pi 1t, because 1 Hz component has to be calculated. Now, so this 1 Hz component will results only for the 1 Hz component inside ft. So 1 hertz component inside ft is cos 2 pi 1t. So if we integrate it, cos 2 pi 1t with cos 2 pi 1t, the result will be 0.5t. So now, as our amplitude of this component was 1, this is the 1 hertz component inside ft, its amplitude was 1, but still we are getting 0.5 t. So to cancel this 0.5 t, we have to divide it by 0.5 t, this term. So what we are doing, to get exactly 1, we will divide it by 0.5 t, that is a1. Similarly, for a2, that is, what is a2 is nothing but 2 hertz component inside ft, of course 2 hertz even component, because it is a2. Had it been b2, then 2 hertz odd component. So 2 hertz even component inside ft. For this a2, we can easily write 0.5 t integration over time t ft cos 2 pi 2t. So again, this cos 2 pi 2t will result in the value of 0.5 t only when ft is 2 cos 2 pi 2t, because it will only respond to the 2 hertz component. Like this, for generalization, we can write an is 1 by 0.5 t integration over time t ft cos 2 pi n t dt. Here we have assumed that our frequency is 1 hertz, because the duration of the signal was 1 second. But suppose if the duration is not 1 second and frequency is not 1 hertz, suppose the frequency is 2 hertz, duration is 0.5 second and frequency is 2 hertz. In that case, there will be integer multiples of 2 hertz, 2 hertz, 4 hertz, 6 hertz, 8 hertz, like this. So f0, that is fundamental frequency, and its integer multiples, and f0. If n is 2, then 2 hertz. If n is 3, then 6 hertz. If n is 4, then 8 hertz, like this. So instead of writing n, for generalization, we can write n f0, because frequency is there f0. If it is 1 hertz, it's well and okay to write n only, but it could be anything. So the general practice is to write n f0. So that is the value of an. Now for calculating bn, same procedure is followed, and we'll have the formula for bn as 2 over t. Actually, we used to write 0.5 t. 0.1 by 0.5 is nothing but 2 over t. So we can write either this or this. In books, generally they follow 2 by t notation. So we'll write bn is equal to 2 over t integration over t ft sine 2 pi n f0 t dt. This is bn. There is one term again. Generally we used to calculate a0 and b0. These are the value of coefficients a and b when n is 0, we are evaluating it separately. So let us see what will happen for a naught. A naught will be integration over t ft into cos 2 pi n f naught t. 1 by t will be the factor. Now when n is 0, this term will become 0. All this term will become 0. We know cos 0 is 1. So a naught will be 1 over t integration over t ft dt. And b naught, similarly b naught will be 1 over t ft sine 2 pi n f naught t. N is 0, so sine of 0 is 0, so b naught is 0. So concluding this, we can write the formula for trigonometric Fourier series as ft is representation with a0. This a0 what we calculated here is nothing but the average value or DC value. So a0 plus b0 is 0, so no need to write hist. Now n is equal to 0 we have calculated, so now limits will start from 1 to infinity. An cos 2 pi n f naught t plus bn sine 2 pi n f naught t, whereas a0, this term is very important because it is the main formula for Fourier series. In this we are reconstructing this ft from sinusoids, so this is called as synthesis formula. Now to calculate an and bn, we are having for an 2 over t integration over time t ft cos 2 pi n f naught t dt. Here we are analyzing this ft, so these formulas of an and bn, they are called as analysis formulas. So it is ft bn 2 over t integration over t ft sine 2 pi n f naught t dt, and a0 is calculated as 1 over t integration over t ft dt. So to analyze any signal we need to remember these formulas. These two formulas are called as analysis formulas, whereas first formula was called as synthesis formula. So this an, they are representing the even components inside the signal, and this bn coefficients, they are representing the odd components inside f of t, whereas this a0, it is representing the DC value or average value, one and same thing, of f of t. So this is called as Fourier series in the trigonometric representation. The next topic will be to study the exponential Fourier series. In next video we'll study exponential Fourier series and how it is derived from trigonometric Fourier series. Thank you.